An invariant point is a point on the graph that is shared between the original function and the new transformed function. So for example, let's say we have a function y is equal to f at x written in green over here, and then we reflect that function over the x-axis, y is equal to negative f at x. This point here, which is shared by both the parent function and the transform function, this here is the invariant point. And anytime we make a transformation, more specifically a reflection, then we were going to very likely have at least one invariant point, but you can have more than one invariant point. And so if we're asked to solve for the invariant points between the original function and a transform function graphically, that is probably the easiest because you could just graph both equations and you just look for any points of intersection, kind of like what we did over here, where the points of intersection are the points that are shared by each new function. So this one is simple. Now, there is a generally predictive way that this happens. If we have a function y is equal to f at x, and we reflect it over the x-axis by giving it the negative a value, you would end up, and of course we're approximating here, we're not actually plugging it into our calculator, you would have something that looks like that. Well, whenever there's a vertical reflection, what we could say is that the invariant point is always going to be at the x-intercepts. What that also means is that y is equal to 0. So the invariant point of a vertical reflection, or reflection over the x-axis, is going to be whatever the x-intercept of the original function was, and then the y value is going to be 0. So it's always going to be in the form of, if I think about my invariant point or my IP, it's x-intercept and then y equals 0. Now, let's say there's a horizontal reflection, and again, it doesn't matter what type of function we're doing here. I chose linear because it's the most straightforward, but you'll see when we do the other examples that it could really be any of the main parent functions. But let's say we have a horizontal reflection. Y is equal to f at negative x, where there's a b value of negative 1. And so remember that this kind of goes this way and this goes this way. And so we have the function in orange here. What we could see is that the invariant point is at the y-intercept, where the original y-intercept of the function was right over here. And if that's at the y-intercept, then it means that the x is also 0. So then we would write it as the invariant point is equal to your 0 and y-intercept. And that's when there is a horizontal reflection. So let's say we have, again, our original function y is equal to f at x, and I take the reciprocal, which is 1 over f at x. When you plug it in your calculator, you're going to get kind of a weird function, and I'll draw it in red here. It's going to look something like this. Okay, and yeah, it'll be something to that effect. Okay, now the invariant points we can see are as follows. Remember, it's the points of intersection. Now, if I had assigned these values, so let's say that this is about 1, we can see that they're always going to occur at set values. So here's the rule. When I take the reciprocal of any function, there's going to be 2 sets of invariant points. It's going to be the x value, whatever that's going to be. I wrote intercept, but it's not always going to be the case. So it's going to be the x value, which is unknown, which we might have to solve for, and a y value of 1. And then the other will be x value and a y value of negative 1. And I want you guys to highlight these in your notes here. These are going to be constant. And again, this comes from the graph. If you take a reciprocal of anything, you're going to get graphs that do look like this, where they always cross the y at 1 and y at -1 if your original function continues on infinitely, which in the context of what we're discussing here, that's always going to happen. So if you have a reciprocal function, then you have constant y values of 1 and -1, and you can have two invariant points. And so these 1s and -1s are constant, and the fact that there's two invariant points is also constant. Now, how are we going to solve for these? The answer is that we're going to have to use algebra or factor, which is also a form of algebra. So use algebra to solve for these, given that we have these y values. Let's take a look at a couple of examples and see how this works. So for our first example, the function y is equal to f at x is transformed to the function below. Given that there are invariant points, and we're just going to correct that here, describe the location of these points. So my first function here is y is equal to 2x minus 2, so that would be f at x. And then here, the second point, y is equal to negative bracket 2x minus 2. This is going to be the transformed. I'm just going to write trans. Okay, so since we have a negative reflection or a negative value for a, right, for the entire function, then we know that the invariant point, I'm going to write it here in red, the invariant point will be the x-intercept of whatever the original function is. Now we can solve that graphically, or we could solve it algebraically. Now, solving it graphically here, the red is the original graph of 2x minus 2, and then the blue represents the reflection, okay, and it's reflection over the x-axis here. And so what we see is that the invariant point is where the original x-intercept is at 1. And so we have a red line that passes through x at 1 and a blue line that passes through x at 1. And so the invariant points will be 1 and 0 for both. Now, if I'm going to algebraically solve for this point, I can just solve for the x-intercept. Now, for this equation, we know that the x-intercept is when y equals 0. So we can go 0 is equal to 2x minus 2, whereby we can isolate for the x, and it's going to be 2 equals 2x. Right? And we would do this obviously by adding both sides, adding 2 to both sides. And then furthermore, isolating for x, we have 2 divided by 2. And just like we proved graphically, our x value of the invariant point is 1. And that would be where the y is 0. So we have an invariant point at 1 and 0. And so this was done algebraically as well. Now, if I look at the next value here, or the next equation, y is equal to x plus 4, the transformed function is y is equal to x, or bracket negative x plus 4. Here, that represents a negative value for the b, which means that we have a reflection over the y-axis. And so that is going to be the reverse, where we should see an invariant point on the y-axis, okay, or invariant point at the y-intercept. And so let's take a look at the graph of these two and see if that holds true. So what we're going to do is algebraically, I mean, we can graph this, but algebraically we can also set the x to 0, and that's going to be the y-intercept, which would be the y-coordinate of the invariant point. So graphically, we're looking for the point of intersection, right? That's the invariant point. So in red here, I have the original parent function, y is equal to x plus 4. And then I have, in blue here, the function that has been reflected over the y-axis, right? Negative x plus 4. And so we could see that right where the original y-intercept of 4 was, there's also the y-intercept of 4 for the reflected graph. And so that is the point that doesn't change. Now we see that it's along right at the beginning of the x-axis, so it has a x value of 0. So the invariant point here is at 0 and 4.